Coming to resonance and coupled circuits, Unit 4, that is network analysis. The first part is resonance. The resonance and coupled circuits we'll see in this session. Resonance. The resonance can be classified into two types. One is series resonance or parallel or anti-resonance. Series resonance is resonance, parallel resonance is anti-resonance. Series resonance or resonance, you can see, consider an RL circuit or LC circuit connected to an AC supply. By considering an RLC circuit connected to an AC supply, a current will flow, IS will flow in this circuit. That is called series resonance. From the circuit, what is Z? Z is R plus JXL minus XC, where XL is inductive reactance, XL is omega L or 2 pi FL. XL is proportional to frequency, XC is capacitive reactance, that is 1 by omega C or 1 by 2 pi FC. XC is inversely proportional to F. XC capacitive reactance is inversely proportional to F. XL is proportional to F means frequency increases from 0 to the value XL also increases. XL is proportional to frequency means XL equal to 0. If you increase the frequency from 0 to some value, XL also increases. Whereas XC is inversely proportional to frequency. XC is inversely proportional to frequency means if frequency increases, XC decreases, inversely proportional. That is, the frequency at which XL equal to XC is called resonance frequency. If you draw a curve, XL and XC, the two curves will join at one point, that is called resonance frequency FR. It is called resonance frequency FR. At resonance frequency, how to define resonance frequency? The frequency at which XL equal to XC is called resonance frequency. Simply we can remember what is resonance frequency. XL equal to XC, at that point what is the frequency? This graph out we have to draw. XL and XC curves are joined, or XL equal to XC, that is called resonance frequency. At resonance frequency FR, XL equal to XC, this is the condition. What is the condition for resonance frequency? XL equal to XC. If you substitute XL and XC, you will get 1 by 2 pi FL, 1 by 2 pi FC. From that, resonance frequency is 1 by 2 pi square root of LC. This is the resonance frequency condition. Suppose if any circuit is there, for that what is resonance frequency, how to calculate it? FR equal to 1 by 2 pi LC. Basically we will concentrate on coupled circuits only in this chapter. Already we covered resonance frequency. The resonance frequency, how to calculate resonance frequency? 1 by LC radians per second. 1 by LC radians per second. 2 pi is called omega. From that, resonance frequency FR or omega R equal to 1 by LC radians per second. Resonance means at resonance inductive circuit, inductive reactance is capacitive reactance R equal to Z. At resonance Z equal to R. This also one condition, because if you see this equation, XL equal to XC, if you substitute in this equation, Z equal to R you will get. At resonance condition, the circuit acts as pure resistive circuit. That is resonance frequency. Next, resonance condition. At resonance condition, power factor cos phi equal to 0, because only resistor is there. For resistive circuit, power factor cos phi equal to 1 or phi equal to 0. Cos inverse of 1 equal to power factor is unity. The three conditions are there. XL equal to XC, that is one of the condition. Another condition is Z equal to R. What are the conditions for resonance? Z equal to impedance of the circuit becomes pure resistive at resonance, because XL equal to XC. XL equal to XC, if it becomes, resonance will appear. Current I equal to V by R maximum. And power factor cos phi equal to 1. These are the three conditions for resonance. Power factor cos phi equal to 1, because the resistive circuit, pure resistive circuit, power factor is 1. Next, what is phasor diagram? That is RLC circuit phasor diagram we seen in third unit. Third unit is AC circuits. In that, if you consider VR and I are in phase, because our resistor current will be in phase. For inductor current, the voltage will lag. For capacitor, the voltage will lag, whereas a inductor it will lead. We already seen in unit 3, suppose for a normal, if you consider voltage as a reference or current as a reference, current through inductor lags by 90 degrees if it is a pure inductor, that is I. At resonance, XL equal to XC, VL equal to VC, and then Z equal to R, that resonance condition we seen. Find the resonance frequency for the circuit as shown in figure. R equal to 10 ohm, L equal to 0.5 millihenry, 10 microfarad. What is the formula for resonance frequency? 1 by 2 pi LC, square root of LC. We are substituting all the values, then we can calculate 2.25 kilohertz. The R is 10 ohm. R is not considered here because resonance frequency derivative formula is 1 by 2 pi square root of LC. L is 0.5 into 10 power minus 3 millihenries it is, whereas 10 microfarads as 10 into 10 power minus 6, then you will get 2.25 kilohertz. Find the impedance, phase angle, current, power, power factor, power, active power, reactive power, apparent power for the entire circuit. For this circuit, 10 ohm, J 15.7 ohm, 20 ohm, and J 31.4. We have to calculate all this. That is impedance, power, phase angle, current, power factor, power, real power, reactive power, apparent power, all three. How to calculate this? You can see. First, we have to calculate impedance. What is the formula for impedance? Z equal to R plus JXL minus XC. XC is 0 here. Then you can substitute only R equal to Z equal to R plus JXL. 30 plus J 47.1. Previously, these are in series. 20, 15.17, 31.47. These are in series. 20 plus 10, 30. These two are in series. We have added 20 plus 10, 30. J 47.1, 30 plus J 47.1. This is called impedance in rectangular form. This is called impedance in rectangular form. Z equal to, in polar form we represented the same. Z equal to 55.85 at an angle 57.5 ohm. From this we can calculate theta. This is called theta. Z at an angle theta is phase angle 57.5. First one answer. Second one answer. First one answer is impedance. Second one is theta, phase angle. Next, current I equal to V by Z. That is Ohm's law for AC circuits. I equal to V by Z. V by Z. Polar form only we have to consider the Z because division will be done in polar form only. That we have to consider. The current I equal to V by Z. Next, power factor. Power factor is cosine of the angle between voltage and current, or power factor of the phase angle, cos of phase angle. Cos of theta, cos 57.5, this is the power factor. Active power is the power consumed by, active power is the actual power consumed by the equipment or circuit. Active power is defined as the product of voltage and current and power factor. All we substituted. Power equal to 96.220 watts. Reactive power is the product of voltage sine and sine phi. Real, you know the power triangle first. Power triangle is, this is phi. The angle is, this is real power P, reactive power Q, and this is complex power S or apparent power S. From that, reactive power Q, if you want to calculate, VI sin phi, S equal to VI, formula is, apparent power is, formula is VI. VI into sin phi, you will get Q. Apparent power S equal to VI, we calculated. Like that, problems will come. Next, another one. If two capacitors are connected in series, what is C equivalent? Capacitor series means parallel combination we have to consider. Resistors. Similarly, Z equal to R plus JXC. This is about frequency resonance. Bandwidth. What is bandwidth? Bandwidth is the difference between higher cutoff frequency minus lower cutoff frequency. The range of frequency over which the signal can transfer, that is called bandwidth. It is the difference of higher cutoff frequency and lower cutoff frequency. Simply, what is bandwidth? The difference between two frequencies, higher cutoff and lower cutoff, f2 minus f1, where f1 is lower cutoff frequency. Okay. Now we will see that resonance bandwidth. You can see here it is the lower cutoff frequency, it is higher cutoff frequency. From that, bandwidth equal to f2 minus f1. Next, we will see quality factor. Another important 2 marks question will come from quality factor. Quality factor is defined as the energy stored in inductor to energy dissipated per cycle. Quality factor is Q equal to 2 pi into energy stored in inductor divided by energy dissipated per cycle. It is also called figure of merit. It is defined as the ratio of inductive reactance to the coil resistance, XL by R. XQ quality factor is defined by the ratio of inductive reactance to its resistance. Energy stored in inductor to energy dissipated per cycle. Energy will be dissipated in resistor, energy will be stored in inductor, that is 2 pi into energy stored divided by energy dissipated. Quality factor is the figure of merit of a coil. For inductor, what is quality factor? Q equal to XL by R for inductor. For capacitor, what is the quality factor? XC by R. This formula you have to remember. What is quality factor? It is the ratio of energy stored in inductor to energy dissipated per cycle into 2 pi. The quality factor plays important role. How much the coil can, suppose a coil is there. This coil, how much energy will be stored and how much energy will be dissipated. This coil has inductance L and small resistance R also. Due to inductance property, energy will be stored. Due to resistance property, energy will be dissipated. How much energy will be stored, how much energy will be dissipated, that indicates quality factor. Similarly, for a capacitor, the capacitor XC by R gives quality factor. Quality factor 1 by 2 pi FC into R. Relationship between quality factor and bandwidth at resonance frequency. What is the relation? Write the relation between quality factor and bandwidth. You know that resonance frequency is 1 by 2 pi LC. Bandwidth is f2 minus f1, that is Q equal to quality factor equal to 2 pi FL by R. Divide the two equation, bandwidth and resonance frequency, f2 minus f1 by fr, R by 2 pi FLR, then you will get quality factor equal to resonance frequency by bandwidth. This is the relation. See the relation. This 2 marks question will come. What is? Write the relation or derive the relation between quality factor and bandwidth. Quality factor Q equal to resonance frequency by bandwidth. That is resonance frequency. What is voltage magnification? It is defined as the ratio of voltage across inductor or capacitor to the supply voltage is called voltage magnification. Magnification is voltage across inductor or capacitor to the supply voltage. Q equal to VL by V. VL equal to VQ. Quality factor Q equal to VC by V. From that, VC equal to voltage across capacitor equal to quality factor into supply voltage. Next problems, so many problems are there. Find the quality factor of the coil for the series circuit consist of resistance R equal to 10, L equal to 0.1, capacitor 10 microfarads, and also find resonance frequency bandwidth. You can see this problem solution. The circuit consists of RLC. RLC circuit, R is 10 ohm, L is 0.1 Henry, C equal to 10 microfarad. Quality factor, resonance frequency, bandwidth. These three we have to calculate. Quality factor is indicated by Q, resonance frequency is FR, bandwidth simply we can indicate BW, Q equal to XL by R, quality factor we can calculate, FR equal to 1 by 2 pi LC, that is resonance frequency we can calculate. Next Q equal to XL by R, 2 pi FR by L, 2 into pi is 3.14 into FR, resonance frequency FR equal to 159.25 divided by R. From that quality factor is 10. If the quality factor is more than 10, it is a good coil. Bandwidth is F2 minus F1. From that quality factor, the relation we can calculate. Find the quality factor for resonance frequency and bandwidth for the circuit. For the circuit, you can see here. Similarly, we go for parallel resonance or anti-resonance. The parallel resonance or anti-resonance. Now we go for coupled circuits, which we left in the unit 4, that is coupled circuits. This is parallel resonance. Let us see quality factor. Energy stored in inductor per energy dissipated per cycle. Quality factor does not have any units. Quality factor also called as figure of merit. Coupled circuit will go now. That we left in previous chapter. Third unit also similar to this. Third unit basics are important for this. Yes, you can see here coupled circuits. Coupled circuits in the sense when two circuits are coupled, when two coils are coupled, the energy will be transferred from one coil to another coil. This is one coil, this is another coil. When you give the power supply for here, a current will flow due to magnetic flux produced by this coil. A current will flow in this coil also. That is, an EMF will be generated in this coil due to this coil. That is called coupled circuit. Coupled circuits are those when energy is transferred from one circuit to another circuit, one coil to another coil, that is called coupled circuit. Types of coupled circuits: conductively coupled circuit and magnetically coupled circuit. Conductively coupled circuit is this one. When directly voltage source is connected to resistor or inductor, then it is called conductively coupled. Inductively coupled is a transformer. A transformer inductively coupled circuit. A transformer acts as inductively coupled circuit, conductively coupled circuit. Conductively coupled circuit and mutual impedance we'll see now. In unit 4, in two-port networks, unit 5, impedances we seen. Conductively coupled circuit and mutual impedance we will see now. Most of the electrical circuit elements are conductively coupled. The impedances Z12 and Z21 is common for both loops. You can see it is Z12, it is V1 and V2. The impedance between this and this is Z12 or Z21. It is Z11, Z22. The impedance Z12 or Z21 is called common for both loops, that is called mutual impedance. From that only mutual inductance will come. Z12 or Z2 is called mutual impedance. What is formula for Z12? V1 by I2. Here Z12 is V1, 2 is I2. Impedance always is the ratio of V1 by I2. Mutual impedance is part of 1 equal to the ratio of voltage at one port to current to another port. You can see here voltage in one port to current in another port, that is called mutual impedance. Due to voltage in V2 and current in I1, that is called mutual impedance. Due to current and voltage in different locations, mutual impedance of the port 1 is equal to the ratio of voltage V2 by I1. Voltage V2 by I1. Always mutual impedance or mutual inductance consider according to the voltage in one circuit to current flowing in another circuit. Due to the current flow in I1, V2 by I1 gives mutual impedance. We can see Faraday's laws. These are important for 2 marks. The Faraday's law is also important for 2 marks. First law states that whenever current carrying conductor placed in the magnetic field, Suppose if it is a magnetic field N and S, North Pole and South Pole, you can see here. Whenever a conductor placed in a magnetic field, assume that it is a conductor. Due to the flux linkage between North Pole to South Pole, an EMF will be generated. Whenever current carrying conductor placed in a uniform magnetic field, an EMF will be generated, that is electromotive force will be developed. That is Faraday's first law. Define Faraday's second law. This electromotive force is calculated by, or it is the EMF induced in a conductor is proportional to the rate of change of flux linkages. Phi is the magnetic flux. How much the flux is changing, that magnitude of induced EMF E equal to minus n d phi by dt. N indicates that according to Lenz's law it is, where n is the number of turns, phi is the flux in Weber, t is the time, E equal to n d phi by dt is the Faraday's second law. Faraday's first law is whenever current carrying conductor placed in the magnetic field, an EMF will be generated. That is Faraday's first law. Second law is minus n d phi by dt. The negative sign will represent the direction of induced EMF is opposing the current. Negative sign represents the direction of induced EMF. This can find by using Lenz's law. What is Lenz's law? Lenz's law states that it opposes the cause. It states that the EMF induced produces a current which opposes the rate of change of flux. The EMF induced produces a current. This current opposes the EMF induced. That is Lenz's law. Self-inductance and mutual inductance, these are important in coupled circuits. Self-inductance is defined as, due to the current flow in this coil, what is the inductance? Self-inductance. Suppose a coil is there, only one coil or two coils. Due to current flow in this coil, an inductance will appear. It is defined as induced voltage in a current carrying conductor when current changes in this current. Suppose in a current flowing through this, an EMF will be generated. That EMF changes when current changes. That is called self-inductance. It is defined as the induced voltage in a current carrying wire when current changes itself. That is self-induced EMF. Self-induced EMF, mathematically we can write Faraday's law, V1 of t equal to L1 di1 by dt, di of I1t by dt. V2 of t equal to L2 di2 by dt. Suppose two coils are there. This coil current is I1, this coil current is I2. The self-inductance is L1. The voltage V1t equal to L1 di1 by dt. V2 of t equal to L2 di2 by dt, where L1 and L2 are called as self-inductances. Self-inductance of first coil and second coil. Mutual inductance is different. When current flowing in this coil, an EMF will be changed in another coil. That the effect of one coil current in another coil is called mutual impedance, or mutual inductance. It is the property of that one form of two coils produces a common magnetic flux which links with the other coil. It is the property of that is formed with two coils produces common magnetic flux links with other coil. Transformer works on mutual inductance. Whenever the supply is given in one winding, due to that common magnetic flux links with other coil produces an EMF. That is mutual induction principle the transformer will work. You studied in B3E. Mutual inductance is the principle of transformer. Let us consider two coils L1 and L2 having voltage applied to V1 and V2. Previously how we have seen two coils L1 and L2, inductance V1 is the voltage applied here, V1 is the voltage applied here, and V2 will get output as another coil. This is the transformer. Transformer have common magnetic core V1 I1. We studied in B3E. According to Faraday's law, V1 of t equal to m into di2 by dt. V2 of t equal to m into di1 t by dt, whereas m is called mutual inductance. Mutual inductance is the inductance which produced by one coil current in another coil. Units of self and mutual inductance can be represented by Henrys only. self and mutual inductance both we represent. Derive the mathematical expression for coefficient of coupling. This is very important for mutual inductance. Coefficient of coupling is denoted by K. How much the two coils are coupled. Suppose coefficient of coupling, two coils are there. These two coils, how much they are coupled from one to another. Because due to this magnetic flux is flowing in this coil, two coils, how much they are coupling. Coefficient of coupling, it is the amount of coupling between two inductively coupled coils can be expressed in terms of coefficient of coupling. The coefficient of coupling is K equal to M mutual inductance divided by square root of L1 and L2, where L1 and L2 are the self inductance of the two coils and M is the mutual inductance. This is the definition of coefficient of coupling. It is very important. Define coefficient of coupling. Derive the mathematical expression for 5 marks. Or 2 marks question is, what is coefficient of coupling? When two coils are connected, then the amount of coupling between two inductively coupled coil expressed by K equal to M mutual inductance divided by square root of L1 L2. What is mutual inductance? When current flow in one coil produces inductance in another coil, that is mutual inductance. L1 is the self inductance of the coil, L2 is the self inductance of another coil. If K is less than 1, it is not a perfect. K equal to 1, it is a perfect coupling. If K is greater than 1, it is very good. K maximum value is only 1. If K is high value, mutual inductance is always high. If K is low value, mutual inductance is always low. From the equations previously, V1 equal to L1 di by dt. We know that V equal to L di by dt. The formula is voltage across inductor is V equal to L di by dt. You already remember what is voltage across inductor. V1 L1 di1 by dt plus mutual inductance into di2 by dt. That is V1. V2 equation is L1 di2 by dt plus M into di1 by dt. That is V2 is the voltage across another coil, that is due to the current change in coil 1 and mutual inductance. This we have to remember. We can download the PDF from the link description to derive this. Okay. You can see here. Let us assume T equal to 0, I1, I2 also equal to 0. The total energy is P equal to dW by dt, or total energy P equal to dW by dt, or energy equal to P dt. The energy is P dt, energy equal to VI dt. The total energy substitute in equation 1 and 2 in above. These two equations we substituted here. Watt power equal to P, actually the total energy P equal to dW by dt. Energy is, power is the rate of doing work. From that, power equal to dW by dt. From that, energy equal to P dt. The total energy is, substitute equations 1 and 2 in this equation, then you will get coefficient of coupling K equal to M by square root of L1 L2, square root of L1 and L2. That is coefficient of coupling, or mutual inductance M equal to K into square root of L1 L2. Coefficient of coupling for iron core is high value is 0.99. Coefficient of coupling is higher value. Find the mutual inductance and coefficient of coupling. You can see one problem. The coefficient of coupling for air is 0.4 to 0.8. The coefficient of coupling for air is 0.4 to 0.8, whereas coefficient of coupling value is 0.99. Let us see another problem. If two inductively coupled coils having self-induced inductances 50 millihenry and 20 millihenry, L1 and L2 are given. Self-inductances are 50 millihenry and 200 millihenries. If the coefficient of coupling is 0.5, K equal to 0.5. Find the value of mutual inductance. What is the maximum mutual inductance? L1 and L2 are given, K also given. Mutual inductance formula is M equal to K L1 by L2. Simply remember K equal to mutual inductance by M divided by square root of L1 L2, square root of L1 and L2. from this formula, mutual inductance M equal to K into L1 L2. Substitute all values, then you will get 50 millihenry mutual inductance. Maximum mutual inductance is for K equal to 1. We have to substitute K equal to 1. Maximum mutual inductance will get 1 by square root of K into L1 by L2. Maximum mutual inductance is 100 millihenries. At maximum mutual inductance, K equal to 1. That we have to remember. First, we have to understand what is mutual inductance, what is mutual impedance also. Analysis of series and series coupled circuits. Coupled circuits. Suppose two coils are directly we can connect by aiding polarity. Suppose it is the dot indicates that current enter. Again dot indicates that current enter. The two dots are joined. In this two inductive coils will be same direction. Current will be. Series opposing means we have joined these two coils in different manner. Current enters here dot mark and leaves. Again current enters same dot mark, but it is oppositely connected. This is series opposing. When two coils can connect in series aiding and series opposing. When two coils are connected like this dot mark, it is series aiding and series opposing. Phi is the total magnetic flux. Phi equal to L equivalent into I. Phi equal to L equivalent into I. Total flux. Total flux phi equal to phi 1 plus phi 2. Total flux phi equal to phi 1 plus phi 2. But what is this? Where phi 1 is flux developer in first coil, phi 2 equal to L I1 plus M I2. This formula we have to remember. Phi 1 equal to L I1. The difference is L equivalent equal to, suppose two coils are connected in series aiding, L equivalent is L1 plus L2 plus 2M. This equation we have to remember. When two coils are connected in series, when two coils are connected opposing, then what is L equivalent? Total inductance or equivalent inductance is L1 plus L2 minus 2M. This we have to remember. Next we will see parallel connection of coupled circuits. When two coils are connected parallelly, L1 and L2, currents are dividing. Let us consider self-inductance of will add the mutual inductance. Total current is I1 plus I2. We multiply above equation, we by d by dt, di by dt equal to di1 plus di1 by dt plus di2 d2. We know that voltage across first coil is V equal to L1 di by dt plus M into di2 by dt. When two coils are connected, the voltage across first coil, now voltage across second coil. In parallel connection, V equal to V1 plus V2, V1 equal to V2. Parallel voltage is same. The same is substituted here. L equivalent is L1 L2 minus M square by L2 plus L1 minus 2M. L equivalent. And two coils are connected parallel. Similarly, this one, analysis of magnetic circuits, we will see later. Reluctance and differences between electrical circuit and magnetic circuits. That is the end of the chapter. Okay, from this, what is mutual inductance? We seen mutual inductance at resonance frequency conditions. We seen, and what is resonance frequency bandwidth and coupled circuits. What is mutual inductance? Mutual inductance M equal to the current flow in one coil. The current flow in one coil V1 of t equal to mutual inductance into current in second coil by dt. One coil inductance, self inductance it is. Due to current flow in another coil, what is the inductance? That is mutual inductance. This is about resonance and coupled circuits. You can find the link in description to download the notes.